Okay, let's quickly do a simultaneous play game theory payoff matrix problem. So I've got player one and player two. Player one strategies are ABC. Player two strategies are X, Y, and Z. The blue numbers represent the payouts for player one, and the black numbers represent the payouts for player two. If player one chooses X, what's best for player one? That would be to get 4. So I'm going to circle that. That's with strategy A. If player two does Y, what's best for player one? That's to go get the 3. And then if player two does Z, 3 is going to be the best with strategy A. Notice player one is never going to choose C. So for player one, C, strategy C is dominated, meaning they're never going to choose that. Now let's do player two. I'm just going to highlight theirs in yellow. And if player one does A, then player two is best off to do Z because they would get 2. If player one does B, they're best off to do Y because they would get 4. It's the best case for player two. And then player one's not going to choose C. Just in case they did, though, player two would be indifferent between X and Z. So in this case, there's 2 Nash Equilibria. That's the case where neither party has any incentive to change, or you could say it like it's the most likely outcomes when they choose based on their own self-interest. So one Nash Equilibria is that player two does Y, player one does B. The other Nash Equilibria is player two does Z, and player one does A. Neither player has a dominant strategy because whatever they choose, their response is based on whatever the other player is doing.